Hello, everyone, and welcome to this presentation on asset management and machine learning. My name is Samuel Idowu, and this is a joint work with Daniel Strüber and Thorsten Berger. This diagram represents a simple illustration of a machine learning process lifecycle, and it shows the sequence of activities that ML practitioners follow when developing ML models. An outstanding characteristic of this process is the experimental nature of model development, which requires multiple iterations before obtaining optimal models. The sequence usually starts with some analysis, followed by the data-oriented works, then the model development works. Here, depending on the obtained model performance and the objective of the ML experiment, users may revisit earlier steps to make updates before proceeding to other steps. The same is true for the DevOps-related stages, where it is often required to make adjustments on earlier steps to effect changes in production. In production of systems with machine learning components, updates and experiments are usually frequent and can be up to several iterations happening within a day or even an hour. In a similar fashion, for non-production scenarios such as ML experiments in research or competitions, where models are not deployed, the number of experiment iterations carried out before obtaining optimal models can easily be in their tens or even hundreds of iterations. As an example, the number of entries, which indicates the minimum iteration count by top participant of a competition on the Kaggle platform, gives us an idea of how large the number of ML experiment iteration can be. The implication of this is that users at some point do have large number of various versions of different assets used during ML experiments, and are usually faced with the cumbersome task of managing these constantly evolving artifacts and data. When compared to traditional software engineering, we believe that there is a gap, since the support tools that are currently available for ML practitioners have not yet measured up to those available for software engineers. For software engineers, we have effective tools that offer extensive asset management support during the entire software development lifecycle. From previous studies, we know that this tooling gap is a big challenge for ML practitioners. For example, in a field study, a large number of participants revealed that they have to rely on custom tools or use ad hoc or informal method when developing ML-based systems. Another study stresses the fact that the high-quality tools which are available for traditional software engineers are not sufficient when developing systems with ML components. Similar to these previous studies, we also believe ML engineering requires a new set of tools and techniques to scale the ML development process. And hence, we define asset management as an essential aspect of realizing this. We define ML asset as a discipline that provides the methods and tools for managing ML assets as structures to facilitate and support user operations and the activities involved in the development, the deployment, and the operation processes of ML-based systems. We also define ML asset as a set of diverse artifacts and data that users need to manage when engineering or developing ML-based systems. When we looked into this problem area, we see a need to improve the situation, and for this, we need to understand the state of the art. That is, we need to understand the current tools landscape and evaluate the support they provide to users. Our investigation led us to the ML experiment management tools, which are a set of tools that are introduced to provide asset management support for users. These are the set of tools that we consider to currently have the best ML asset-specific management support. We believe that in order to advance research in developing new tools and methods, it's important to have an empirical understanding of these tools. As in this work, we carried out a survey on experiment management tools that are used in practice and present our findings using feature model syntax. We define our research questions as follows. First, we are interested in the data types that are tracked by the tools. We want to identify how the assets are collected. Third, we are interested in how the assets are stored. Then we want to have an overview of the supported operations on the tracked assets. Then lastly, we want to identify the type of integrations the tool supports. For our methodology, we carried out a systematic search to identify our candidate tools. We used DPLP, ACM Digital Library, and Google Search Engine as our data source and defined search queries based on our research questions. We defined and applied a selection criteria that resulted in 17 final candidate tools and analyze them based on the tools provided in the tools documentation. This table shows the final candidates for our data analysis. Here we have 9 cloud-based tools and 8 standalone software tools. and they vary from open source to for-profit tools. The results from our analysis is in form of a feature model syntax, which has the following top-level features that corresponds to our research questions RQ1 to 5. The top-level features are asset type, collection, storage, operation, and integration. The asset type include resources, software, metadata, and execution data. Resources represent asset types that are required as input or produced as output from an ML workflow stage, while the software asset types are those used for the implementation of machine learning processes. The metadata assets provides descriptive static information about the ML experiment and its dependencies, while execution data are those that users choose to automatically or explicitly track during experiment execution. I will now show examples of how some of the subject tools support some asset types. A log data frame function is used here to track a data frame as data sets, while the function log artifacts in these examples are used to track arbitrary files as generic resources. The function log metrics here tracks model accuracy as execution results. Under the feature operation, we have the Explore, which allows users to derive insight on their ML experiments and the obtained results. We have the version operation through which users can create checkpoints of the experiment and restore to earlier versions as needed. The Manage operation allows users to manage asset dependencies, to manage process execution and modify assets or even delete some assets. We have the Execute, which indicates support to execute experiments and rerun prior experiments, while the Feature Access indicate means to read or retrieve stored ML assets. Lastly, the Feature Collaborate indicates support for collaboration-related operations. For our findings, the key operation is Explore, as it is supported by all the tools to analyze and compare experiment results. Many of the tools allows users to track assets of any type without differentiating the asset types. Many of the tools depends on traditional version control systems for managing certain assets such as script files. We believe this contributes towards the tooling complexity and may in fact affect the adoption rate of such tools. The explicit approach of asset collection, which is required for most tools and where users have to instrument their code, has its drawbacks such as the overhead cost and proneness to human error. We expect future tools to address this limitation. Our presented feature model, which represents the variability of our subject tools, can benefit researchers who want to contribute towards the next generation tools and techniques for ML engineering by providing an overview of the state of practice support. Our results also provides ML practitioners with an overview of the ML asset management supports currently offered by existing tools. As future work, we intend to extend this study to account for prototype tools from scientific publications. To conclude, practitioners working with ML-based systems deserve tools with better support for management of ML assets. We carried out a survey on 17 tools with asset management supports that are used in practice to enhance our knowledge of the problem space. Lastly, we established the asset types, the collection approach, and the operations that are supported by the candidate tools. For further details, please take a look at our paper. Thank you for listening.
Welcome to everyone. Today we have the session named Deep Neural Networks, General Issues. And the first paper of this session has been presented by Samuel Idowu, who is here to answer any question. The paper is called Asset Management in Machine Learning, a Survey. So please use the chat to ask for any questions regarding this paper. I'm going to start asking to Samuel. So my first question is, did you apply any quality criteria on this review or not? And what criteria did you apply?
We applied some quality criteria, and as it's actually shown in the paper, we had some external, as we discussed in the internal validity, for example, in the selection of the tools, since we used the manual approach to avoid bias in the selection. We had to use multiple source of selection or source of data. So we considered the selection using multiple literature or bibliographic, multiple literature databases. So yeah, that's one of the approach we considered for improving the quality.
Okay, thank you. Another question is regarding your subjective idea. It's not a very technical question, but a more subjective question. It's about how do you feel about the poor adoption of machine learning from the point of view of the industry? Because maybe the machine learning is very well established on the academy, but I don't know why the adoption of this proposal in the industry is not so high at the moment. So what do you think about this poor adoption of machine learning in industry could be?
So similar to the focus of the study, I think my comment will be from the perspective of the tools and the support that the developers or machine learning experts have currently, which is when we compare it to traditional software engineering, there's still need for a lot of improvement. There's a big gap in the amount of support that is currently available and what we really desire. So I think this could be one of the limitation or one of the problems that is currently affecting the adoption of machine learning in the industry, because so far, there are not standardized approach to developing machine learning systems as we have for traditional software engineering. So it's still largely based on intuitive and experimental approach. And we emphasize that there will be needs for supporting tools to actually improve this sort of processes.
Yes, my question is because, I don't know, maybe the tools are not so powerful enough to for example, to provide an easy learnability or to provide a guidance for the user. And maybe if these tools in the future are improved in that sense, maybe the adoption in the industry can reach a higher level. I don't know.
I agree with you. I agree with you.
Okay. Another question is about the tool that you use for the literature review. Because in the paper you specify that you have read paper from eXplore or ACM repository. And my question is why you didn't try to use any tool like Scopus that try to gather different libraries such a way you can automate the process.
So I guess the main reason for that is that for this work we were interested in tools that are used in practice, and a lot of those tools are actually not do not have research publications. So that I would say that's the main reason why we also considered the 3 different sources with Google Search Engine as one of the sources, because the foremost interest is to actually acquire as many tools that are actually used in practice. So this is one of the main reasons why we did not consider Scopus, for example.
Okay. My next question is about future work, because usually a systematic review is a first step in a very long way.
Yes.
So what are your next steps in the closest future?
Yeah, so this is just the first step, trying to understand the kind of support that the tools that exist today provides for users. And what we're working on is to contribute towards next generation tools and support or techniques for developing ML-based systems. So the idea is to take information from this paper, the result of this paper, and apply it towards future work in developing next generation tools for ML, for management of machine learning assets.
And is it part of a PhD thesis or is a postdoc?
This is part of a PhD thesis, yeah.
Okay, so if there are no more questions from the attendees, from my part, this is over. So thank you very much, Samuel. Very interesting work.
Thank you very much.
So a virtual clap for you. And please wait for the next presentation that is going to start in 3 minutes, okay? So see you in the next one. Bye bye.
Bye.